All right, today we're going to be talking about chapter 17. We're going to be starting a new section that's all going to be about the atmosphere. And so what we're going to be doing in chapter 17 is looking at the different gases in the atmosphere and just kind of an overview of weather. So when we start taking a breath of air, we see that we're not just breathing oxygen. Our bodies use this oxygen, but the vast majority of what we're breathing in is in fact nitrogen. Um, the breakdown is about 78% nitrogen, 21% oxygen, which gives us about 1% left for all the other gases. The vast majority of that last 1% is argon. Uh, Now, you may have heard a lot about carbon dioxide in the atmosphere, and it's steadily increasing. Currently, it's about 0.04% of the atmosphere. And that 0.04% is mentioning, as I mentioned, is increasing, but it is in fact vitally important when we get to uh, greenhouse gases. We'll talk about that later this chapter. And then the remaining fraction of a percent is going to be all of the other trace gases, um, things like neon and methane, ozone, um, and you can see the list of trace gases there on the screen. Now, what I'm looking at here is dry air. Water in the atmosphere can vary between 0 and 4%, but it's so varied. What we're looking at here is just dry air. So what's the most abundant gas in the atmosphere? At 78%, the answer is nitrogen. Now, air is very unique in that it's easy to squeeze and expand. And when we start looking at this squeezing and expanding, this makes air very, very different than, say, water and liquids and gas and solids. And so when we start looking at this air, um, this expanding and contracting can actually has an impact on the temperature. One of the unique properties of our Earth is it contains water in 3 states here at the Earth's temperatures. And so when we start looking at water in the atmosphere, it exists in all 3 states as a gas, um, in a liquid, and as a solid in ice. And so we can see that water in the atmosphere exists in all 3 states. Um, when we start looking at uh, aerosols, now the definition of an aerosol is a tiny liquid or solid particle that can remain suspended in the air. So these are very, very small. That little kind of little mu sign is microns. And so we can see that's 1 micron across for a scale of this little bit of volcanic ash there. We also have some pollen, um, a little bit of soot there, and some sea salt. Note the halite structure there of that sodium chloride. So when we start looking at these particles, these are all examples of aerosols. Now, most of the time when I say the word aerosol, a lot of people think I'm dealing with spray cans of hairspray or paint. And those, in fact, are aerosols. They're small particulates which can stay suspended in the air. Uh, and so they are, in fact, aerosols, but they're not the only ones. There's a lot of natural aerosols. So what do we call a particulate, whether it be organic or inorganic, that can stay suspended in the air, whether it be a liquid or a solid? It is an aerosol. And so one other aerosol that we have here is dust. And so we can see a dust storm off the Sahara Desert, and that dust can travel all the way across the Atlantic Ocean and have its impact here in the United States. And we can actually monitor those aerosols there. Some other aerosols are bits of smoke. And when we start looking at this smoke, um, again, these particulates are incredibly small, but they can remain suspended in the air, and they're vitally important to the atmosphere. Um, when we start looking at uh, clean rooms in hospitals, we want to make sure that, in fact, it does not have any of those aerosols because we don't want those little aerosols getting into, say, an operation. And so if you wanted to operate in a clean room, you'd have to remove all of these aerosols. And so these are very, very, very small particles. And so you can do this uh, by cooling that air down. Now, I have a standard soda bottle here, and in the soda bottle is a little bit of water in the bottom. And so what's been happening in this water bottle is the air inside this container is has a bunch of that water. And so let me open this up. And so as I'm opening up this water bottle or this soda bottle, I'm going to put some aerosols in here. I'm going to use just a match. And the smoke from this match is going to put a bunch of aerosols in there. And these aerosols are incredibly small. Now, these aerosols are incredibly important because these aerosols, in addition to being particulates in this atmosphere, what they're going to allow us to do is provide water to condense onto these. And so I'm squeezing this water bottle. This is sometimes called, as a standard experiment, it's called a cloud in a bottle. But I have this little container that I'm squeezing. And as I'm squeezing this, we'll learn about the ideal gas law of this chapter, that temperature and pressure are intricately related. So an increase in pressure is similar to an increase in temperature, effectively an increase in temperature. So by squeezing this, I'm causing more water at the bottom of this to go into a liquid state or into a gaseous state. And then if I release this, I can actually make it turn into a cloud. It needs these cloud water droplets need an aerosol to condense onto. So by squeezing it, I can turn it clear, on, off. And what I'm doing here is in this cloud in a bottle here is I'm using these aerosols. Now, some of these aerosols can be a bit of a problem because if we have too many of these aerosols can produce photochemical smog. And again, this can be problematic. Ozone is also going to be directly associated with this photochemical smog, which is an irritant for people at the Earth's surface. Now, when we start looking at the atmosphere, that 78% nitrogen, 21% oxygen is currently what we have here. But that's not always the case. Remember in our chapters on the Earth's history, we talked about the planetesimals all forming together to form large planets. And so if this planet was made up of materials from our nebula, then we'd expect the gases to also be from that nebula. And so when we start looking at the gases in the early part of our atmosphere, what we had is mainly hydrogen and helium. And so when we start looking at the first atmosphere, it was primarily hydrogen and helium, maybe a little nitrous, methane, and nitrous chemicals there as a result of the concentration of gases formed from the accretion of our planet. Now, when we start looking at these particulates, the Earth we do have a volcanic activity, some comets coming close enough to the sun that they would actually start to vaporize, and those gases would be liberated, which could make their way back onto the Earth's atmosphere. Now, the second notably different atmosphere occurred after the late heavy bombardment of our planet ended, and the Earth's surface cooled off. And when the Earth's surface had cooled off, we could actually have liquid water on the Earth's surface. And so the atmosphere was primarily nitrogen with about 20% carbon dioxide. Now, when we start looking at the carbon dioxide in the atmosphere, this abundance of carbon dioxide was taken in by photosynthesis. those cyanobacteria we learned about being some of the early life on Earth would take in carbon dioxide and give off oxygen. And so having this liberated amount of oxygen, you'll recall that we had the banded iron formation occurred at the Great Oxidation Event, where that oxygen in the atmosphere was taken back out of the atmosphere as it interacted with the iron at the Earth's surface. And so when we started looking at the atmosphere, it was predominantly nitrogen. And then during the second oxidation event, we had an abundance of oxygen. Again, once we bound all of the available iron with this oxygen, the oxygen levels were allowed to increase again. And so when we start looking at when did the atmosphere, when did oxygen begin to accumulate at a more than trace quantities in the Earth's atmosphere? That would have been the Great Oxidation Event. So when we start looking at the atmosphere, we can see that the atmosphere has changed in the past, but these days it's pretty consistent. So when we start looking at atmospheric properties, these are things that you'd find at a standard weather station. And so I've got a standard weather station. Mac has, I don't know how well you can see the weather station that we're recording. Almost all of these bits of data out here on the college, at the campus. And so I've actually pulled up a weather report for today. The data from our closest weather station that is recorded in part of NOAA is at the Farmington Airport. And so we can see just about all of the different bits of information. The first one that we're going to be dealing with is air temperature. Most of the rest of the world deals with Celsius. We use Fahrenheit here in the United States. We can start looking at atmospheric pressure, the weight of the overlying air pushing down on us. We can look at relative humidity, which is a measurement of how much moisture is in the air at a given temperature. We can look at wind speed and direction, visibility, how far can you see, what type of clouds and what's the cloud cover? Is it fully clouded or is there partial clouds? Is it isolated clouds? And then finally, precipitation. And so when we start looking at all of these different, the state of the atmosphere, and these different measurements are telling us the state of the atmosphere at a given time, this is what is defined as weather. We can look at weather over a longer period of time, and we'd call that climate. So again, I've pulled up the weather from NOAA's webpage, looking at what the weather is going to be looking like right now as I'm recording this, as well as what the weather is going to be looking like in the future, and that's called the forecast. And so we can see this on the bottom here of what the forecast is going to look like. So when we start measuring air temperature, it's a state at which these molecules of air are actually vibrating around. You may have heard about absolute zero, negative 273 degrees Kelvin, or 0 to Kelvin, negative 273 degrees Celsius. When we start looking at air temperature, we never get down to this absolute zero where these molecules literally would not be moving at all. They would be perfectly still. But the faster these molecules are moving, the higher the temperature. And so we have a couple of different thermometers here on the right, or thermometers, measuring temperature, how fast these atoms are moving around. The one on the left is Fahrenheit, the one on the right is Celsius, and in the middle is the conversion to go from Celsius to Fahrenheit. The one underneath there with the K is Kelvin. Kelvin is just 273.15 degrees off of Celsius. It's the same conversion. So if you were going from Fahrenheit to Kelvin, you'd have to go from Fahrenheit to Celsius and then Celsius to Kelvin, the easiest way. But so we can see these two standard temperatures here. The lowest temperature ever recorded is negative 89 degrees Celsius, or negative 129 degrees Fahrenheit. Water freezing at 0 degrees Celsius and boiling at 100 degrees Celsius, or 132 and 212 degrees Fahrenheit. Um, the highest air temperature ever recorded is 134 degrees Fahrenheit, or 56 degrees, 56.7 degrees Celsius. And so there is the standard relationship. I prefer using the word Celsius because it's a nice, easy units to measure when we start looking at temperature. 100 centigrades is the difference between water freezing and water boiling. So it's all based, just like the metric system, on water. Um, so some common values there. And so we can look at the state of the atmosphere in terms of its temperature. And we start looking at this temperature, it's not very uniform throughout the atmosphere. And so one of the things that we will end up doing is to do a atmospheric sounding, where we'll take a weather balloon and measure the air temperature as we go up in the atmosphere. When we go up in the atmosphere, we're going to have less air pressure. The weight of the overlying air is going to drop. And so Torricelli had a barometer, the first barometer, and this was actually using a tube of mercury with a tube of mercury that you would actually have one area capped. You'd fill the mercury up and you'd flip it into a tube of, into a little pool of mercury. And so the weight of the mercury, it's a heavy liquid, would actually start to sink to the amount of air pressure that was pushing down on that pool of mercury. What we have here is a little bit more, a meter of air pressure has a little spring in here, and it's doing the exact same thing as pushing the air, surrounding air is pushing on this spring. And if we don't have a change in elevation, these barometers will actually measure small changes in air pressure as a result of atmospheric conditions that change. Now, if we really wanted to change the air, we could take this and put it up higher in the sky or closer to sea level. And so that is going to have a real dominant effect. And so all atmospheric measurements of air pressure are moved down to what the air temperature would be like at sea level. Because if you were measuring the air at a high elevation and air at a low elevation, you'd have a huge difference, and you'd always have that difference. But if we normalize everything, what is the air pressure at sea level, we could actually compare air in different locations. And so here's a little visual showing the difference in air pressure and elevation. And I'm sure you've all experienced situations like this, where if you change air pressure, particularly if you're close to sea level, a little bit of elevation change means a lot more change in air pressure. You're going through a lot of that air that's squeezed together. You may have experienced this if you've gone on an elevator in a tall building and you're going to feel your ears pop as the pressure inside your ears are trying to balance with the air around yourself. You can do this in airplanes. This is also why if you were throwing a football or a baseball at altitude, the ball will travel a lot further. I know of some professional athletes that would actually start living at higher altitude. And as a result of this, their body would have to deal with the lack of oxygen. And so their bodies would adapt to this lack of oxygen. And then when they actually competed, if they competed at sea level, their bodies would have this influx of extra amount of oxygen that they would be able to draw on. And so when we start looking at air pressure, again, the higher you go, the less air pressure we're getting. And so what we're looking at on the bottom there is millibars of pressure. And again, that is one unit of air pressure. We could also look at inches of mercury, again, going back to the Torricelli condition. So what is the pressure of the overlying air? Because the dominant force of air pressure is a change in elevation, you could actually figure out how high above sea level you are based on your atmospheric pressure. And so if you had a barometer, it could also tell us how high above sea level are, and then technically it would be called an altimeter. But that's what an altimeter is actually using, is measuring the air pressure. So when we start looking at the next calculation or the next thing, for those in the lab class, this is what you're going to be dealing with is something called relative humidity. And this is the amount of water vapor um, in the air divided by the air's capacity for holding water vapor. I think of relative humidity, and it's always in a percent, as like a gas gauge. If I told you that I have 50% on my tank of gas, does it tell you a whole lot? It tells me that I might want to start thinking about going to get some gas, um, but it's not going to tell me how much water vapor I actually have in the air. It's just telling me how close it is to being full, or how close my tank is to being full. Um, and so when we start looking at relative humidity, it's a measurement, just like a gas gauge. It tells us how close is the air to being full. And so we have a couple of different examples here that when we start looking at hot air, it can hold a lot more water than cold air. The atoms are vibrating around more, and so it's allowing you to hold a lot more uh, water in the air. And so when we start looking at the uh, 4 examples on this screen here, on a foggy, chilly day, we see at 10 degrees Celsius, air is full of water, and so full that it's actually creating condensation in the atmosphere on those aerosols. On a cool, dry day, again, the air's a little warmer, and so it can hold more air, more water in the air. When we start looking at a warm, humid day, again, there's a lot of water in that container. But if we compare, it's a hot, dry day on the right on a hot, dry day, we can see that that hot, dry air um, has, because the air is a bigger flask there, can hold more water, um, it's going to have a smaller gauge. It's going to have a smaller relative humidity, but it may in fact have more water than on the foggy, chilly day. Um, the only difference is the temperature again. And so when we started looking at lab, we will be dealing with measuring this relative humidity, how much water is actually in the air at a given temperature. And so the amount of water vapor in the air divided by the capacity for holding air is called the relative humidity. And when we start looking at, you may see words that you may have seen before here. This term dew point is the temperature in which you have to cool air down to get dew. So if I wanted to use this example here of these different beakers, if the increasing beaker represents an increase in temperature, bigger temperature can hold more air. If I wanted to have the same amount of water in the air, if I cooled the air down, I'm going to cause that balloon to, or that beaker to get smaller and smaller and smaller. If it got down so small that the air couldn't, or the container couldn't hold the water, we've hit that dew point. It cooled the air down to the temperature in which dew or frost would start to form. So when we start looking at weather, the other piece, one of the other components that you're going to be measuring is the wind speed and direction. The horizontal movement of air is called wind. Air moving up is updrafts, air moving down is downdrafts, air moving horizontally is wind. When we start looking at wind, winds are always named at the direction in which it's coming from. So a wind out of the north would be a wind from Canada going towards the Gulf of Mexico. A wind out of the south would be just the opposite, from the Gulf of Mexico towards Canada. Most weather systems that we have here in Missouri are coming from the west as a result of these global winds called the westerlies in this area. So when we start looking at winds, we can use a weather vane to tell us which direction the wind is moving, and that's the big the big tail on the back here that's catching that wind, showing which direction the wind is coming from. In this case, it's coming from the north. And then those little cups on the bottom is called the cup anemometer, which is actually measuring how fast the wind is moving. Think of it as a pinwheel. The faster, it doesn't matter which direction that wind is coming from, the more wind that is, the faster the wind is moving, the faster those little cups are going to get grabbed and spun around. And so we can actually translate that to the actual wind speed. And so when we start looking at wind, we do want to know what is the wind speed and the wind direction. So when we start looking at the property of speed and direction is measured with a weather vane and an anemometer. Don't use a thermometer to measure the wind speed or direction. So when we start looking at winds, they can move water and atmospheric conditions from one place to the next. When we start looking at air, we can see how far people can see in the atmosphere, and this is known as visibility. And this is the distance from which a person with normal vision looking through the air can identify objects, and it would be the visibility, and it's usually given in a distance, how far they can actually see. We start looking at the atmosphere. We have cloud cover, which is an estimate of how much of the sky is obscured by clouds at any given time. And so here's an image, a composite satellite image of the Earth showing cloud cover. And this is a fairly standard cloud cover. I do want to point out right around the equator, seems like we have a belt of air, and that's not uncommon. Right about 30 degrees north and 30 degrees south latitude, we don't have a belt of air. And then about 40 to 60 degrees, we've got another belt of clouds in both north and south of the equator. We'll talk a little bit more about these here in just a second. So we start looking at precipitation, water coming out of the atmosphere. We can measure that water, and unfortunately, my kids left some buckets and toys outside over the last week, and we had some rain, and so they inadvertently made a rain gauge, a container that contained or that measured the amount of water at that given time. And so what we have here is an exact similar situation here that's showing the amount of rain over a given time. Now, this funnel is going to provide a bigger, better, accurate readings. It also, if we had snow and we melted the snow, we can measure that amount of water in the atmosphere. And so we start looking at total precipitation is a cumulative amount of liquid material or solid material that's turned into a liquid that fell over a specified period of time. So the 24-hour total precipitation or 36-hour or event that caused when the rain started to when the rain stopped. And so we can measure this over a period of time. And so when we start looking at weather stations, here's a standard weather station. I mentioned Farmington is our closest weather station here at the college. Meteorologists have a set of instruments that automatically measure the temperature, dew point, wind speed, direction, visibility, cloud type, coverage, precipitation, and intensity. And so we have this vast network of information that is constantly being gathered. And the site I was looking at for this information is the NOAA's weather page. NOAA is the National Oceanic and Atmospheric Administration. It's a great place to collect all of this data. And then at these weather stations and throughout the United States, this is measuring in North America and South America, it's measuring the atmospheric conditions at the landscape, or shortly right above the Earth's surface. You can notice that it's away from a building where our weather station here, we're collecting this data, but it's on our roof, which is great, but it's not an official weather station because our roof got some blacktop on it, or black surface, which is going to increase the temperature where we're measuring. And so it's not as accurate, so it doesn't meet the standards to be an official weather station. We can also collect the same information with a sounding, which is basically a balloon, and we measure we fill this balloon with hydrogen or helium, and then this balloon will rise up because it's less dense than the air around, and it'll actually measure the information, the same bits of information. I kind of want to look at the temperature in particular. If we were to do one of these soundings, we would now, when we start looking at the atmospheric conditions at any given point, we take one of these balloons. This balloon is going to rise up, and the lack of air pressure is going to cause this balloon to expand, and then eventually that balloon would pop and fall back down, and we can repeat the process with this weather station. And so when we have one of these weather balloons, if we were start to go up in altitude, we'd notice the temperature drops. And so we know that the Earth's surface is the area that's heating up because sunlight is hitting the Earth's surface. It's heating up the air around it. We know that hot air is less dense than cold air, and so this hot air is going to start to rise up. And if this hot air rises up, eventually it's going to, now it's no longer near that Earth's surface, so that heat is going to be lost, and so the air will sink back down. As a result, this air is constantly turning over. The word troposphere means turning over. And so when we start looking at the troposphere, this turning sphere, the higher you go, the cooler it gets. But eventually what we're going to end up with is that air mixing. And this is where we have weather. So the temperature is decreasing as you increase the altitude in this troposphere. What's going to happen above the troposphere is we end up with this stratosphere. Now, the word strata means layer, so we have a layered sphere above the troposphere. The boundary is called the tropopause, where the temperature pauses. And then in this next layer, what we have here is the stratosphere. So in the stratosphere, the UV light hitting ozone in this stratosphere. Stratosphere is marked by an increase in ozone, where this ozone is getting vibrating around, giving off more heat. And so the higher you go, the warmer it's going to get. We know that hot air rises, and so the top of the stratosphere is the hottest portion. The lower portion is not as hot. We know that hot air rises, so it's going to stay very, very segregated. And so very little vertical movement occurs in this stratosphere. This is why there's a series of layers of atmosphere, hence the name stratosphere. Now, once we move away from the ozone, an increase in altitude is going to cause this air to expand, and this expanding air is going to decrease in temperature again. And so we have this layer called the mesosphere, meso meaning little or middle sphere, where you have a decrease decrease in temperature with elevation. And then when we get out into the thermosphere has an increase in temperature with elevation. And what's happening here is where the solar winds are striking any particulates of air. Now, the air in the thermosphere is in fact hot. If we measure a particle of air there, it's vibrating around really fast. By definition, that is the temperature. But if you went out into this thermosphere, the air is incredibly, incredibly thin. So there's a little bit of air that's really, really moving around. So it is, the temperature is really high, but the pressure is extremely low. It wouldn't necessarily feel hot like it would be at the very bottom of this layer here. In this thermosphere, we have high concentrations of charged gas particles called the ions. And so this is where we have the ionosphere. This is really important. We start looking at radio waves that you can bounce off of this ionosphere. So which of the atmospheric layers, which layer of atmosphere is characterized by temperatures that decrease in elevation temperatures that decrease as elevation increases? You go up, the temperature goes down. Well, that would be of the list, that would be the troposphere. Um, Now, we have in the stratosphere an increased amount of ozone during most of the year. But we realized that we could expand and contract gases, and we learned to master these quite a bit, especially we had these gases that were very, very effective at expanding and contracting. So we could actually manipulate the temperature, just like I did with this little bottle here. And if we used chlorofluorocarbons, these were gases that were really easy to squeeze and really, really easy to expand. And so, and they also didn't interact with the human body. So these things were great. We could put them in anything, and they just drifted out into the atmosphere. We didn't really worry about them until we realized that they interact with the ozone. And as a result of interaction with the ozone, um, they actually are very effective at breaking down the ozone. As a result, they created the ozone hole at this South Pole during the winter months. And so human activities have caused the concentration of ozones to decrease in the South Pole in its winter, in the North Pole in its winter. And so in 1980, we realized that um, part of the problem. And so we had, as a joint group of countries, developed the Montreal Protocol, which stated that we're going to cut down on the amount of chemicals that can cause holes in this destruction of the ozone, this decrease in the ozone. And we have seen, in fact, we're rounding the bend now, and we are in fact seeing a decrease in. We're not seeing the ozone hole get any larger. We're actually seeing it start to shrink back down. And it's still there. We still have to kind of finish through this cycle, but we're seeing some progress on the ozone hole. It's not getting any bigger. It's rounding its bend, and hopefully it'll get a little bit smaller. Layers defined by chemical composition and electrical charge. And so when we start looking at these, not looking at temperature, the lower portion of the atmosphere from the troposphere, stratosphere, and mesosphere are pretty uniform. The homosphere is this well-mixed mixture of gases. Again, slight increase in the stratosphere where the ozone is, but by and large, it's a pretty uniform, homogeneous mixture of gases. But then when we start looking at the heterosphere, this is the layers in this really, really thin air as a result of molecular weight differences in different gases. And so when we start looking at a helium balloon, if we pop this helium balloon, the helium is much less dense than the air around it, than the nitrogen and oxygen around us. So it'll actually rise up and leave the Earth's surface. We call this escape velocity, and it has a really, we don't have as much gravitational mass to keep those light gases here on the Earth's surface. And so the helium is really it's usually trapped in the same places that we trap oil. And so if we're trapping oil, we'll commonly separate off the helium. And for a while there, we put it into a container in a mountain in Texas. And we're actually using more of this helium for medical use devices, as we mentioned, doing things like changing the air temperature and getting rid of those aerosols, cooling the air down, getting all those causing all the moisture out of the air and any of those particulates to adhere to those moisture droplets. This would, we're using a lot of helium as a result of this. And so as a result, there's actually a helium shortage right now. And when the demand goes up, and the supply goes down, the price goes up. And so we're seeing an increase in price in the last couple of years as a response to the supply and demand of this mined gas called helium. The last part of the atmospheric layer is the ionosphere. Is a layer that contains relatively high concentrations of ions, these positively charged or negatively charged subatomic particles. And again, these are really important for radio waves, that we can actually bounce the radio waves off of these ions in the atmosphere, in the ionosphere. And so we can actually get a signal when we start looking at AM and FM waves bouncing off of this ionosphere. So one other unique property in the atmosphere that we have are related to these ions is our auroras, aurora borealis or aurora solaris, which we have high energy particles from the sun being pulled towards the North Pole or the South Pole due to the magnetic field generated from the Earth's core. And so as these high energy particles from the sun are moving towards the Earth, they're causing this light here that we're seeing here in the aurora borealis or aurora solaris australis in the southern hemisphere. And so these can have different colors and dancing through the atmosphere with these lights. One other portion in the atmosphere is clouds. Now, we talked about visibility and cloud cover, but we can also talk about the importance of clouds in that they are in fact suspended droplets of water or ice. Even in the summertime, you can have ice particles in the atmosphere. Remember, the higher you go in the troposphere, the cooler it gets. But these are going to be suspended in the atmosphere. They're suspended because they're incredibly small. So these clouds are really effective at reflecting light, scattering some of this light, and in some cases absorbing light. Thin clouds appear whitish, thick clouds look more gray or dark. And so there's a number of different ways that the air, you can form these clouds where air has to get cooled to that dew point temperature. And so when we start causing maybe a front moving in, what's going to happen is the air in this image here, from this cold front, the air is pushed up. When warm, moist air is pushed up, it gets cooled off. And if it cools to the dew point temperature, it's going to cause clouds. When air gets pushed up over a mountain, again, same, the higher you go in the troposphere, the cooler it gets. If you hit that dew point temperature, it's going to be causing the clouds to form. In this case, we've got colder ground and warmer ground, a little thermal occurring here, some differential heating of the Earth, where this warm surface here is going to cause this air to rise up. The air around it is cooler. It's going to push that air up, and we have some unstable air here. And this is known as lifting. When air is getting pushed up, it is going to cool to the dew point temperature, and so the air is going to become saturated. Now, clouds are defined on their altitude and shape, and there's all kinds of different clouds that we can see here. Clouds are very, very effective at being a predictive of what the upcoming weather is going to be like. They can produce precipitation, and again, altitude and shape are the three different ways you can identify clouds. So when we start looking at clouds in the high portion, and these are about 6 kilometers or 280,000 feet above the Earth's surface, these are going to be really cool environments, and so they're going to be almost always ice crystals. And so the air is cold up there, it can't hold much water, and so these tend to be very, very thin, wispy clouds. And because it's so cold in those areas, there's not much water to begin with. So these are going to be too high to produce precipitation. The mid-altitude clouds, or alto clouds, produce that are between 3 and 6 kilometers in height, or 10 to 20,000 feet approximately. They can either be stratus or cumulus clouds. And again, they're going to be too high and thin to produce precipitation. Again, air the higher you go, the colder the air is going to be. So what kind of clouds are 3 to 6 kilometers above? Mid-latitude clouds, also called alto or stratus clouds. So we start looking at these clouds here, these mid-latitude clouds. The word strata means layer, alto meaning middle. Cumulus are those puffy clouds, and we have cirrus are these thin, wispy mane's tail, mane of a horse, thin wisps of clouds. We have low-lying clouds, which can produce precipitation, and these are the stratocumulus or strata clouds, low-lying clouds. Then we have clouds that are also towering, that start at the Earth's surface or right in this low range and can go all the way up to the top. These would be called cumulonimbus clouds, towering, puffy rain cloud. So we have, in this case, here's an image of a lenticular cloud, a lens cloud. When this air mass is only pushed up in a small location here, creating this lens cloud associated with this mountain here. You can have very unstable air moving around to create mantis clouds and rolling clouds, lots and lots of different types of clouds. Your book calls these unusual clouds. Clouds are primarily based on their altitude and their moisture content and their shape. So when we have clouds near the Earth's surface, we're technically calling these fog. And again, fog clouds are going to be requiring the same thing. You're going to have to cool the air to that dew point temperature, the temperature at which condensate, you have 100% humidity. Cool the air to that dew point temperature. You can do this in a couple of different ways. One is on your, if you had a glass of ice cold glass on a hot, humid day, you're cooling the air around it to that dew point temperature, and that's why you're getting the can or the glass sweating. So in this case, we're having radiation fog. This is occurring when clouds form from the ground, absorb heat from the air above, and cooling the air just above the ground so it reaches saturation. To advect means to move horizontally, to convect means to roll. And so we have air moving in from a different location. And so if we have warm, moist air moving in onto a cooler surface, we call this advective fog. And so the air can actually be warmer than the ground. The ground is really can fluctuate quite a bit in temperature. And so if warm air is moving over a cold surface, it can actually cool the air to that dew point temperature. And so it's advection fog. Then we have evaporative fog when we're adding water to the environment here. And we have, in this case, we have a lake, which is, in this case, a little bit warmer than the air around it. So the water is evaporating. When the water evaporates, it hits the cool air around there. It's going to condense to the dew point temperature to create this fog. Now, when we're dealing with any of these clouds or fog, what we're going to have is water droplets condensing onto condensation nuclei. And so when we start looking at condensation nuclei, these are going to be bits of aerosol. And so, so remember, those aerosols are those particulates in the air, whether they be bits of bacteria, smoke, or salt. And so when we start looking at these particulates, water is going to cool off, and the air is going to cool off, and it's going to provide the air can't hold as much water, and so it's going to precipitate out to onto those condensation nuclei. And so it's going to create these cloud droplets. And you can see in this image, these cloud droplets are quite small. And then finally, what can happen is those cloud droplets can merge to form a drizzle or a small raindrop. Now, in both these cases, I do want to point out raindrops aren't teardrop shaped, they're round. Surface tension is going to cause these water droplets to stay round. Eventually, if they get too large, what's going to happen is the water droplets would trap a little bit of air, and then it would actually break these particulates apart. But then you can still get condensation, coalescence, where these particulates can get larger and larger. So when we start looking at when saturated air is cooled, clouds form because water molecules accumulate on the aerosols to form water drops or ice particles. Now, when we start dealing with cold clouds, we have the same thing happening, but in this case, we're building crystals instead of building liquids. And so what's going to happen is the same thing is happening where we're having single crystals are allowing water droplets to condense onto them, but these crystals are going to become larger and larger to create aggregates of snowflakes. In the case of hail, which is what's going to happen is the air is getting pushed back up, and so these ice particles are going to have more and more surfaces on, or more and more sequences of this air getting blown back up. So when we have water changing from one state of matter to the next, tremendous amounts of energy is either going to be absorbed into the water or released from this water in the form of something called latent heat. Now, the word latent heat means hidden heat. It's heat that's associated with the state change in matter of not associated with a state, a temperature difference. And so if we have 1 gram of water or 1 cubic centimeter of water, and we were to go from solid to a liquid, you're going to have to transfer about 80 calories. Calories is a measurement of energy. When we start looking at liquid to a gas, it's going to be on the order of hundreds of calories for that same droplet of water. And we start looking at water going from 0 to 100 degrees Celsius, it's only 100 calories. So when we start looking at phase changes, you have a tremendous amount of energy that's either absorbed or released associated with this temperature change. This is why you sweat, by the way. By putting a surface of water in the on your skin, when the water evaporates, it's going to absorb a tremendous amount of this latent heat, and so it's in fact going to cool off your body. We see lots of examples of this. If you had air in the summertime going into a basement or into an air conditioning unit, you'd have water condensing out, and that's going to when air going into a basement, what's going to happen is it's going to cool off. It can't handle as much water. It's going to precipitate, and that's why basements can be damp. These phases of energy are going to be really, really, really important when we start looking at mass balance of atmosphere energy. Now, one other kind of important topic when we start looking at temperature and when we start looking at electromagnetic radiation in the atmosphere. And this is electromagnetic radiation, or sometimes referred to as light. Light is just a small portion of this electromagnetic spectrum, but it's a measurement of how energy is moving from the wavelength of it, which energy is moving. And so forms of energy that travel in the form of electric and magnetic fields through space. And so all objects are going to emit electromagnetic radiation. So my body is in fact, giving off this electromagnetic radiation. The sun is giving off electromagnetic radiation. The sun is hotter than I am. And so as a result, it's going to be giving off more electromagnetic radiation, and it's going to be shorter wavelengths. The cooler an object, the less the electromagnetic waves, and the wider the ranges. Now, there's only so many different wavelengths that we can look at, and so our eyes are only adapted to seeing this little bit of visible light. There's a huge entire spectrum here. So when we start looking at things like cell phones and communication wavelengths, they're also traveling on these different frequencies. And so if we tune into the right frequency, we can process that information and get the information that we want to see. So if we're using a cell phone, a radio wave, a television wave, these are dealing with these different wavelengths. And so there's only so many of these different wavelengths that we can operate on. And so the FCC will actually say you need a permit to operate on just this very specific wavelength. And that's what you're allowed to use. And so you own that wavelength. If you are, say, channel 2 or channel 5, you're allowed this certain frequency. And so there's only so many of these different wavelengths that we can apportion out. And when we start looking at these shorter wavelengths, things like gamma rays and X-rays, these are really, really hot objects that generate these. And they also have a lot more penetrating power the shorter the wavelength. Now, we start looking at something called the black body radiation, in that radiation, a body absorbs energy and must be radiating this back into space. Otherwise, the object would continuously heat up. So we have to bring in and bring out the same amount of energy. And now it can be different wavelengths, but it is in fact the total amount is going to be the same. And so if we start looking at the sun, that we're getting sunlight, and that's going to be a shorter wavelength. And so we are in fact giving off longer wavelengths in the form of heat waves. The warmer the object, the shorter the wavelength. And so if we start looking at visible light here, we have the shortest wavelength of visible light that we can see is blue. The longest would be red. Beyond red are the infrared. Shorter than blue are the shorter than violet are the ultraviolet. So when we start looking at our atmosphere receives UV light and visible light. The UV light gets caught for the most part in the ozone layer, and is either absorbed or reflected in that stratosphere. When we start looking at the Earth's surface, what's hitting the Earth's surface is shortwave visible light. And so what's going to happen is that shortwave visible light is going to be converted into longer wave heat waves. And so the darker the object, the more absorption that is going to occur. And so a black sidewalk is going to be absorbing more of this radiant energy than, say, a bright light colored surface. And so what's going to happen is the thing that can absorb a lot of that sunlight is going to convert it into the heat waves. And so then it's going to get hotter. Things that are white light reflecting a lot of that sunlight, and so it's not absorbing as much, and so it's not going to get as hot. And so these newly longer wavelengths are going to be absorbed into the atmosphere, and so sunlight can pass through different gases. And so when we start looking at this chart at the bottom here, water vapor, carbon dioxide, ozone. But we start looking at carbon dioxide, it is very, very, very effective at blocking out longer wavelengths. When we start looking at shortwave radiation, carbon dioxide isn't as great as at blocking it out. And so as a result, it is water vapor and carbon dioxide are very, very effective at allowing sunlight to come in and not allowing heat to get out. So the greenhouse effect is important that it does allow liquid water to exist on surface of the earth because it allows the Earth's temperature to be very, very stable. At night, when we don't have sunlight, the fact that we have water vapor and carbon dioxide, it keeps the Earth's temperatures significantly warmer than we would have if we didn't have those greenhouse gases. It does, let's see, it keeps the Earth's surface from reaching its radiative equilibrium. Yeah, it is, in fact. There's a lag where we are holding back some of that heat at night. And so it's not hitting, it's constantly cycling as the Earth is spinning, changing the amount of heat on Earth. The greenhouse gas effect is important that it allows the Earth's surface to be much warmer than it would be without the greenhouse effect. And that is a very true statement. Without the greenhouse effect, we would not have liquid water on Earth. It would not be warm enough to have liquid water on Earth currently. So the answer is all of the above. So when we start looking at things like electromagnetic waves and its relationship to the sky, shorter wavelengths are more easily scattered than longer wavelengths. And so when we're looking through the sky at noon, what we're seeing here is a lot of the scattered sunlight, and the short wavelengths are going to be those shorter wavelengths. And so this is why the sky is blue. At sunset, we're looking through a lot more of that atmosphere. And so as the Earth is spinning around in this image, the lower portion of we're going through a lot more of this atmosphere. So we're going to scatter out a lot of the blue, but what we're going to have left is a lot of those red, oranges, longer wavelengths. And so when we start looking across the horizon, this is why sunsets and sunrises tend to be oranges and reds, and skies can be blue. So we can also end up with mirages. A mirage is an image formed from when light is reflected from an object bends through the atmosphere, so it actually seems to appear something that doesn't actually exist. And so a mirage on the desert highway here is associated with the bending of this light, associated with hot air. Now we can also do this with the bending of cold air, where the path of light is being bent down as a result of the cold air below and the warm air above. So when we start looking at water droplets, we know that water droplets are very important. We start looking at a rainbow here. And so when we start looking at sunlight, what's going to have to happen is you're going to have the sun behind you. You're going to have enough water droplets in the air that the sunlight can actually bounce off those water droplets and refract off the water droplets. And because these lights are hitting at slightly different angles, what's going to happen is shorter wavelengths are going to refract out differently than longer wavelengths because of the curvature of the water, because of the curvature of the water. Pardon me. So we can see on this lower image here that this, as the sunlight is coming in, what's going to happen is the sunlight is, or water is going to, sunlight is going to hit water at different densities. And because we have water at a different density than air, it's going to refract light, just like the physics, the same physics that caused P and S waves to refract through different layers of the Earth. And so when we have these different wavelengths traveling at different speeds, they're going to refract different angles. And so the difference in refraction of these angles is going to cause the separation of those different colors. Now, as these water droplets are refracting at different angles, it's creating its own rainbow. Every rainbow does have a secondary and even a tertiary rainbow as these lights are refracted. We just don't always get to see that secondary rainbow in many cases. You need to have more water droplets in the air, and you need to have vivid enough sunlight. So capturing the second and even the third rainbows are a little bit more difficult. So if you have any questions, let me know.